Hello, so good afternoon, everyone. I hope you've had a great day so far with the event. I saw that there were a lot of interesting talks before this one. Um, but here I am now to present to you my talk entitled Generating and Navigating Through Language Parse Trees Using Python and Tree Setter, presented by me, Lagras Tairalada. And I did not create a slide for like an introduction to me because I didn't think it would be too important for the talk, but all that you need to know about me is I am from the Philippines. I'm currently studying at college, University of the Philippines. I'm incoming fourth year. I'm gonna be in my fourth year this school year. That would make me 21 years old, and I'm going to be also starting this next school year. I'm also gonna be working for a. I'm gonna be working as a DevOps engineer. So that's all you need to know about me. Um, so I'm here as part of the PyCon Taiwan track. So of course the talk topic is gonna have Python in it, but the talk itself doesn't necessarily center around Python. So if you're not that familiar with Python, you should be okay here to listen. And I hope, sorry, yeah, there will be occasionally some cars that will be passing. So I'm sorry if that's gonna be loud. I'm gonna try to repeat whenever that does happen. I'm gonna repeat what I say. Okay, so let's start. So who here knows about regular expressions? Ooh. I don't think I'm actually gonna be able to see the audience, but I'm just gonna pretend that I see you guys raising your hands because regular expressions are very prominent when you program. So regular expressions, of course, parses regular languages, and what that means is that these are essentially strings that do not require memory or nested structuring. So plain text, you can think about that as like plain text. How would you use regex? You would use it to match over patterns found in strings of characters, right? So here is an example of a regex that is used. Um, in case that you can't identify what this regex is doing, this is for checking valid email formatting. So um, first here, it checks for valid characters, one or more because of this plus, and then it follows an at symbol, and then valid characters again, one or more, followed by a dot that is escaped because dot means any character that's not white space in regex, and then it's followed by alphabetic characters. Sorry, it's followed by alphabetic characters, two or more of those characters. Okay. And for any computer scientists out there that are interested in a much more technical um, property of regular expressions, it's that they are translatable into finite state machines or finite automata via Kleini's theorem. So that's that's a nerd fact that you can learn about that. So why am I talking about regular expressions? It's that a use case that TreeSetter does tackle is currently done with regex, which is for syntax highlighting. I believe IDEs such as VS Code does use regex for identifying parts of code that then they would highlight. For example, like function names or variable declarations, they would use regex to match over those patterns in the strings themselves. So here's a very poor attempt of me to make regex for patterns found in Go code. So on the left side we have Go code. Don't worry if you don't know any Golang or Go. The syntax is very much C-like, so it should be easy to understand what's happening here. So on the left side, again, we have Go code, and then on the right side, we have, again, a very poor attempt of matching on variables. So here we would have like characters, and then, yeah, we are matching on based on characters. And this is where regex kind of, this is where regex kind of falls apart when you're trying to match on not just strings, but a logical structure, which is what code is. Code is a logical structure. It's related to each other, and you kind of imagine it as sort of this recursive structure wherein you have scopes, and then like inside those braces, that's a function scope, right? And you would like to be able to identify that without having to rely on those characters, and that is what TreeSetter aims to do. So there's actually a much more formal definition on what on what Twister is trying to do, which is because it already exists in automata theory, and it's called context-free grammars. So context-free grammars, in contrast to regular expressions, they parse both regular and context-free languages. So context-free languages are actually still under regular languages in that they are matching on they're matching on strings in characters, but the only difference, the only nuance here is that context-free languages, or like languages that can be defined under context-free grammars, are they utilize recursion and nested definitions. Think regex, but you can assign variable names. So these are very handy in dealing with strings that are context-free, i.e. syntax. Context-free here means that you can try to parse a portion of the string without having to think about anything else from the string. That's what makes it context-free. Despite it actually providing even more context than just regular expressions. More context in the sense that it contains semantic information. You can handle sorry, you can handle nested structures based on just your context-free grammars. These are how language specs are often described in EBNF notation or extended Brachus-Knorr form. So this is how it would look like. This is from the official Go language spec, where it's defining what I was trying to define earlier using regex. And as you can see here, we're not just matching on characters themselves, we're matching on recursive names. So as we see here, short variable declaration is an identifier list followed by this walrus operator, colon equals, and then expression list. And then to know what these identifiers are, these recursive definitions are, you would have to look recursively through the rest of the language spec, and then you would discover there how identifier list is described and what characters describe it. So if we look here below, you see here function declaration uses function body here, and then function body here is defined as a block, and then again that block is defined somewhere else. So this sort of definition using recursive structures, it allows us to understand this piece of text, originally just plain text from regex. We are able to parse it as some sort of tree, an abstract syntax tree. So this is how it would look like. So this is an abstract syntax tree of a method call from the pandas library in Python. So we see here that on the left side, we're storing to this variable traindf, and then we're using pd, which is usually pandas, pd, and then an attribute from pd, which would encode that would be like pd dot, and then read csv. That's how we can represent it in the abstract syntax tree. And then the argument here, which is string, because it's under a call node. So now we're thinking about the text in terms of nodes, and this actually provides us with so many other benefits than just this organization that we see right now. And that is what TreeSetter is trying to take advantage of. So now we have TreeSetter. So sorry. So let's check out. Not let's check out, but I encourage you to check out this wonderful talk at Strange Loop given by Max Brunsfeld about TreeSetter. I'd say that he's much more of an authority on TreeSetter than me because he actually contributed to TreeSetter, and I actually presented this talk topic to PyCon Taiwan as just something that I was very interested about and I was willing to research on and then talk about. And yeah, so if you wanted a much more in-depth look into TreeSetter itself, I would suggest this talk, like highly suggest this talk. It's really good. One of three of the things that he discussed in this talk is properties of TreeSetter. The first one that I'd like to bring up is its incremental parsing. TreeSetter is described as an incremental parser generator, and what that essentially means is that when it parses a file, and you modify that file, it doesn't have to reparse the entire file. It only has to take in your changes, and then it combines that with existing tree, and then it modifies that existing tree based on your changes. Compare this to the regex approach in editors such as VS Code, wherein it would actually have to pre-parse it would have to parse the entire file every time every character you would have to change, and that would make it slower than just doing it incrementally, just like what I've done. Hello, I'm sorry. I didn't notice I got disconnected.
We see you again.
So can you
Hello.
share your screen? Yes.
Yeah, I'm sharing it.
We lost you about 2 minutes. Yeah, this page.
Yeah, which part did I get cut off in?
Yeah, this page.
Okay, so did I mention the error recovery already?
I think yes.
Okay. So yeah. So incremental parsing, it also allows for excellent error recovery because it just puts an error node in the parts where the code is broken, and then when you resolve it, it then just replaces that error node in the tree, and it doesn't affect the rest of the tree. So that's a problem you would encounter with like things like VS Code, right? If you end up writing incorrect syntax, the highlighting for the rest of the code kind of like breaks at that point. But this isn't a problem with Tree because the errors get isolated to that specific node in the tree, and that's really cool. And that's a benefit of incremental parsing. And next up is it has no dependencies like Tree itself. Usually how you would use Tree is you would define a grammar.js, which is in like a JS notation. You would define that in that, and then you would use the tree setter CLI tool to convert that into a parser, and then that parser you would use with its language bindings. So that entire process does not have any other external dependencies, which is really good because if you've been programming for a while, you would know that less dependencies is better dependencies. So lastly is Tricitor aims to have a uniform interface that it can provide for like pretty much all languages. So if you were able to use Tricitor to generate a parse tree for a like Python code, you would also be able to do that for a piece of let's say Ruby code. So that would also work. So so um my first exposure to Tricitor was because of NeoVim, a text editor that I've been using, and Tricitor is very prominent in NeoVim. In fact, it's actually integrated into NeoVim itself, and it gets used for its syntax highlighting, and other plugins use it for various different things as well, such as indentation and folding of code. So is the stream still okay? Because I'm gonna change screens. Okay. So right here I have I'm gonna increase the size since this is probably broadcasted like a projector. So right here I have the NeoVim open. This is an example code that I have prepared, and you can actually see the syntax tree here in NeoVim just by typing this command inspect tree, and this would open up its tree setter tree. So right here we see that it has the matching parse tree for the code on the left side. So in fact, if we even click on parts here, it highlights which parts it corresponds to. So that's really cool. So like if we click here, it also corresponds to here, and that's nice. And the one of the cooler parts of Tricitor that I discovered was that it actually has a query language. You can use this tree to query on the code that you have. So you can do that in UVM as well by doing edit query as a command, and then that would open that there. Let's actually move it down, and then let's shrink it a bit. Okay, so if we try to match on a function declaration node, then we assign a name to it, let's say a function, you see that it gets highlighted here. So all of the function parts of the code gets highlighted and it gets labeled. So that's really cool, right? So it's in a sense, it's kind of like regex, wherein you can match over parts of your code, but you're using the syntax tree of the code itself. So because we see here that it's not matching these because these functions are actually method declarations in Go, and we can make it so that it matches that by using an alternation, again just like in regex, by alternating over function declarations and method declarations. This would match now, and if we look over here at our main function, it matches again. And then for the queries themselves, you can even specify the field. Sorry, you can even specify the fields. Like if we go here, name, and then identifier, and then we would label this as function.name. Oh, not here. We label this as a function.name. We can even select on just the names of the functions themselves, and then we can add a condition. So like if we want that the function name should always only be equal to main. So now if we highlight this, this doesn't highlight this anymore because this is a function, but it's not named main. But the methods here, the method down here, is still highlighted because again it's in an alternation, and that's really cool. Again, we're only using the syntax tree, and we're already matching on a much more comprehensive manner than just using the characters themselves in regex. Yes, so that would be the NeoVim demo. So next is language bindings. Okay, so as I mentioned earlier, you define the parsers using grammar.js, and then you create a parser using the tree-sitter CLI. It would generate you a C file, and that would be used as the parser for the languages. And then you can then use these language bindings, which are like kind of like what we were doing in NeoVim, but you can do it programmatically. Think of it as like an API for the parse trees of whatever parser you give it. So this language bindings comes in pair with parsers of the language that you want to be querying upon or like want to walk. So these are the supported ones, and then these would be the pre-built parsers that tree-sitter provides. So you don't have to define the grammar.js for the languages that you want to query on. So that's what NeoVim was using earlier. It was using the Go parser that was defined by tree-sitter, and then I was querying it using the binding that was provided in NeoVim. And then now we have PyTree-sitter. So for this section of the presentation, I'm actually just going to be going over the documentation or like the README, because I think it's very much detailed enough for the talk here. So here we see that we're just going to be installing tree-sitter for Python, and then we install a parser, just like what I presented earlier. We install a parser that's provided to us, or we create our own parser, then we can use that here in our language binding as well. And then it's just a matter of creating a parser object and then providing the language object that was from our imported parser. So again, imported parser, then you put that in a language object, and then you make a parser object for that language, and then that parser object can then be used to parse bytes of code that you want to be that you want the abstract syntax tree for. Then there are different ways. Sorry, I can't really control the road. I'm just gonna wait it out. Okay, so they provide different ways to parse over bytes here. You can either use the byte offset or points, which is essentially rows and columns. I'm gonna increase the font size for the people in the audience, for the people in the room. Sorry, and then the resulting tree object, you can just straight up uh, access its methods, right? Access its methods or attributes, and that's one way to do that. And I believe this approach is exclusive to the Python binding, because the rest of the bindings, they actually use this cursor approach, you wherein you would get a cursor object, and then here tree cursor object, because this would be much more efficient for walking the tree itself. So you can do go to first child, and then you can check what the type of the node is. Okay, yeah, I'm zooming in even more. Okay, so and then yeah, so here we can see how the incremental parsing happens. So whenever a source file is edited, you can just edit the existing tree, and then you can pass that into the parse. You can parse in the new source with the old tree, and then it would not have to redo the entire tree, and that would be much faster. So that's really cool. Then lastly, for the querying, like what I was doing earlier, there's a query language for tree setter found in their documentation again. So that's what I was following. You can do equal to, any equal to. There's also operators. So that's cool. So you can do that, and then you can match on either captures, just like in regex, or you can do matches, which is a much more organized way of doing it. And that would be all for my tree setter. So tree setter itself is used in so many uh, projects that you can find that are related to code syntax analysis. A new IDE right now, which I believe it's called Z. It was from from the developers of TreeSetter, I believe, and they're using TreeSetter for their highlighting. So that's a very good vouch for TreeSetter. And then there are again various NeoVim plugins that utilize TreeSetter for stuff like indentation, code folding, and also just uh, querying over the code itself. So instead of relying on the plain text, you can use the logical structure of the code. And I believe that's a much more elegant way to handle that sort of sifting through code, because it's much more organized, and it just makes more sense in my head. Personally, it makes more sense that you were using the recursive structure of code to query over it instead of just using the characters themselves. So that would be all for this talk. If you're interested in my stuff, you can check out this link. It's a very simple link. It's also a very simple site because I just did it in one sitting. So that would be all. Thank you. Thank you.
Thank you for your speech. And right now it's a Q&A session, so anyone would ask question to our speaker? If yes, you can come forward to the stage. Yeah. Yes. No, yeah, go here, come here.
Hi, nice talk. I have a question. So you mentioned once we build this syntax tree, we can query. My question is, during the development, sometimes we have incomplete or the code which is not correct in the syntax. So for example, you have typo something in your keyword. So I was wondering, this tree setter can still handle this kind of exception.
Thank you for your question. And yeah, Lada?
As I have mentioned earlier, whenever TreeSetter encounters an error in the code, instead of just breaking the entire tree, it instead puts an error node at that corresponding part of the tree, so the rest of the tree is unaffected. And then whenever you resolve that error, it just replaces that error node. So you can think of the error node as some sort of placeholder. So in that sense, the error is isolated to that specific part of the tree. So that's how we would handle error recovery.
Thank you, Darla. And more question about this topic? Don't be shy.
I'd also like to add that Max Brunsfeld, again, this talk that I brought up earlier, he actually does cover error recovery in much more detail than what I have done right now. So I recommend you check that out if you're interested. So yeah.
Okay, I have one question. If because you start this one, do you have any side project for this one, this tree-seater? For example, translator? Yes.
Yeah, I'm actually going to be using it for my thesis since I'm going to be developing a language and TreeSitter is a parser generator. I'm going to be using that for like generating the parser, like the parser for the language itself. And then I'm going to be using a binding. I don't think I'm going to be using the Python binding. I think I'm going to be using I think it has a Rust binding. I think I'm going to do that. I'm going to use it to evaluate the code from the syntax tree, since I don't really want to be writing my own parser, since it's like much more work than is probably possible in the time frame that's provided to me, which is like half a year or like 5 months. So yeah, I'm going to be using it for my thesis. That's the short answer.
Sure. Any question about this one? If no, I think our audience can ask you question later. Is okay? Okay.
Of course.
Okay. So thank you, Lada, and see you next time. Bye bye.
Bye bye. Thank you for having me.
Thank you.